In this video, we're going to talk about group 7, the halogens. We will talk about why they are p-block elements, and we'll also go into their reactions and their reactivity. They're also known as group 17 on some periodic tables. First of all, why are they p-block elements? That's because if you do their electron configuration, you will find out that they all end with a p subshell. So the highest energy electron is the electron that is last, or the orbital that's last filled, or subshell that's last filled. And you can see it's usually on the right, well, on the right as you write these out. So we can see with chlorine, it's got a p subshell again, with the highest energy electrons, and then highest energy electrons in bromine again. Okay, so all of them have the highest energy electrons in the p subshell. Okay, and they all have 5. So go back to the question, why is bromine classified a p-block element, for example, if you might see in an exam? That's because the highest energy electron, remember you must say highest energy, okay, is in an orbital within the p subshell. If it's a d-block element, it would be within the d subshell, but the same answer, okay, or f block in the f block, f subshell, or an s block in the s subshell, okay, but you have to say highest energy. Now, how does the boiling point change? Well, first of all, they're all non-polar diatomic molecules. So diatomic meaning they come in pairs, and you can see the examples here. Okay, and they're non-polar. Now, the reason they're non-polar is because you have the same element, which means it has the same electronegativity, which means the electrons are in the middle because they pull with the same power. Okay, so that means there's no dipole, which means you have no hydrogen bonding to affect the boiling point, which means that you have no permanent dipole-dipole interactions, which means you only have London dispersion forces. Now, London dispersion forces is determined by number of electrons, and a number of electrons will give you how big the actual atom is, and therefore how big the molecule is. So we can see fluorine here, then chlorine, bromine, iodine, and astatine. Now, the 3 colours you definitely need to remember when they're in their standard state is pale green for chlorine, orange-brown for bromine, and purple for iodine. Astatine is black, fluorine is pale yellow. But the 3 you need to remember are these 3 here, chlorine, bromine, iodine. Okay, so make sure you remember those. Now, as you go down, you can see that the atom is getting larger and larger, which means you're adding more and more electrons. So the more electrons you have, the stronger the London dispersion forces, and the more energy it takes to break them. So if we go into our exam answer, increased number of electrons results in stronger London dispersion forces, which take a higher amount of energy to break. And that results in a high boiling point as you go down. Now, how does their reactivity change? Now, the reactivity is dependent on the number of shells. So the number of shells, as we talked about, increases as you go down. So does the atomic radius. Okay. This is also due to shielding, so the shielding increases with the number of shells. And that means the attraction for the electron being gained decreases as you go down the group, because to react, these molecules need to gain an electron. So let's have a look at that. So we've got a fluorine molecule here, fluorine atom here. Okay, and to react, it's going to want to gain an electron. And for example, metals to react would lose an electron. So here, it's going to gain. So what we're going to do is we're going to get it to gain. So it's the ease with which that electron right there is gained. That's the important thing. How easy is it for it to do it? How much does it do it readily or not? Now, the smaller the atom is, the closer the incoming electron is to the nucleus, essentially, and the more the atom can pull in that incoming electron. And so basically, if you have fewer shells, you'll get an increased attraction, and therefore it'll be more reactive. So the most reactive element is going to be fluorine at the top, and then the least reactive is going to be astatine at the bottom. Now, this happens also with halogens as oxidizing agents. Now, what is an oxidizing agent? Well, oxidizing strength is the measure of the strength with which an atom can gain an electron. Now, let's think about this before we go on. Oxidizing would mean that you lose an electron. Okay, So that means if I want to have an oxidizing agent, I want it to cause something to lose an electron, that means that oxidizing agent must gain that electron. And therefore, it would get reduced. Okay. So when you come across these questions, it's really, really important, and this is our exam tip, that you're always clear on what is being reduced. Use the equation, state the species, for example. There is a difference between F- and F2. So be careful what you're doing. So if we again look at a diagram that we had before, that means this atom here for the fluorine is going to gain an electron, and it's going to gain it very, very, very easily because it has very few shells. Okay, so it can attract that electron in really, really easy. Acetine would not do the same thing. Now on to displacement reactions. A displacement reaction is where you take a more reactive halogen to replace a less reactive halide. The halogen is the molecule, okay, and the halide is the ion. Okay, so we're going to take a molecule that's going to replace the halide within a compound, the ion within a compound. Now to know what's going on, we need to know the colours of the halogens within water and cyclohexane. So if you look here, we have our water at the bottom in all three of these test tubes. Okay, and then we have our cyclohexane at the top. It does that because the water hydrogen bonds to the other molecules and makes it more dense. So the water is more dense than the cyclohexane, which just has London forces that hold it together. So they're weaker, the hydrogen bonds are stronger, so it's more dense at the bottom. That's why the water is always at the bottom layer. So if you look at the colours, you can see that the colours are generally a bit weaker across the bottom and they're a bit stronger across the top. So stronger in the organic layer and weaker in the aqueous layer. That's because the solubility of the halogens is better in cyclohexane, the non-polar solvent. Because halogens themselves are non-polar, they dissolve better in non-polar solvents. That's why you get these stronger colours. Weaker colours in the aqueous because the water is a polar solvent and we've got a non-polar halogen, so they don't dissolve particularly well. Now if we look at this and we go through the colours, we can see that this one is what you would see in a laboratory. But it's a very, 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 very pale green colour. Okay? And this is roughly the same colour in terms of if you've made it really, really concentrated. So remembering that chlorine is a pale green, and we've got that over there. We then go for the bromine, and the bromine is a kind of orangey brown. You can see it's weaker in our aqueous layer, but it's still an orangey brown colour, I say, okay? So both our organic layers and our aqueous layers for chlorine and bromine are the same. We then go to our iodine. You can see in the iodine, you can see that it's brown on the bottom and it's purple on the top. So the organic layer is a purple/violet and the aqueous layer is a dark brown. So we need to make sure that we remember all of these colours, otherwise we can't answer the questions that are going to be in the exam. We're now going on to answer a question using those colours. So we're going to keep our colours on the right-hand side here. Okay, and let's look at the question. So an orange-brown aqueous solution was added to a colourless aqueous salt of sodium. The product produced an organic layer of violet. Let's go back through that again. Orange-brown. So it's saying orange-brown aqueous solution. So we look down at our colours and we can see that an orange-brown is going to be our bromine. So our bromine must be what we add to our sodium salt. Okay. Now, the product produced an organic layer of violet. So we go across again, look, and we say, right, okay, well, the organic layer that's produced is going to be violet. Well, that means it must be iodine. So what we're saying is we've taken bromine, added it to a sodium salt. We don't know what the sodium salt is. And it produced an organic layer of violet. Okay, so if we then look at this and we can go, right, okay, we have a sodium salt. We don't know what that sodium salt is. Okay, and we know that it, for example, is NaX. Okay, we then add that sodium salt and we add it to an orange-brown solution. Okay, so that orange-brown solution is going to be Br2. We have worked that out. Okay, And then we go from Br2, it was added to in a colourless aqueous salt sodium. The product produced an organic layer of violet. Okay, so we've got our organic layer of violet. We know that that is, let's do this, iodine. Okay, so we know we've got iodine, and we know we've got bromine. All we have to do is say, right, okay, that must mean, okay, the iodine must have come from somewhere, which must be, for example, that X. Okay, so that means that that X is equal to I minus. Okay, so X is equal to I minus. And that means that the more reactive, the bromine, which is more reactive, which is going to replace this X, which is I minus, because we know it produced iodine over here, and we know that bromine is more reactive than iodine. Okay, it's going to then bond with the sodium. So that means we go NaBr. Okay, so we found out what our X is. Our X is I minus. Okay, so what we can now do is we can say, right, okay, let's write this properly as an ionic equation so we know exactly what's going on. We can see from this, hopefully, that the Na is doing nothing. So the Na is going Na plus there, it's Na plus there. So I'm going to get rid of that. And I'm going to replace this X for I minus now because I know it's I minus. Okay, and so there is my I minus. Okay. And then I'm going to add that to my Br2. Okay, and then got it here. We've got, remember the sodium is a spectator ion, so we are going to do the Br this time minus, and then plus I2. Okay, so there here we've got our ionic equation where we substituted in the X because we found out what the X is. We worked out from the fact we produced iodine that the iodine must have been over here. It must have been displaced by the bromine because the bromine is more reactive. And that means we can then rewrite it without the sodium because the sodium is a spectator ion. Now what we haven't done is balance the whole equation. Okay, so let's just make sure we balance the whole equation. So we've got 2 bromines here, which means we have to have a 2 here. We've got 2 iodines here, which means, remember, X is iodine. So we'll have to have a 2 here. So we balance it all. If you then pull the balancing down, that means you have 2, okay, and you have 2 there. Okay, so we've got a fully balanced ionic equation and a fully balanced equation there. Okay, now we can then do it into half equations. So we can look at this and say, what's happening to each half? And let's have a look at the half equations. So that means that my 2I minus, okay, is going to go to, again, I2. Okay, and if you look here, there's 2 negatives on the side here. It's totally neutral here, which means 2 of those negatives must have been removed and kicked out. So therefore, plus 2E minus. Okay, and we can then look at this and say, right, okay, that means it's losing electrons. Therefore, it means it is oxidized. Okay, so that is oxidized. And if you go back to previous information that we've given you, if something is oxidized, that means it is the reducing agent. Okay, so that is the reducing agent. Okay, so that is the reducing agent. So we've got oxidized and the reducing agent. Okay, we can then go for the other one and we can say, right, we've got bromine happening this time. Okay, and the bromine, okay, is going to go to, if we look in our equation, 2Br minus. Okay, 2Br minus. And then we can say, right, okay, what's happening with the electrons? Well, I can see neutral this side, 2 negatives this side. Okay, so I must be adding 2E minus because I've got to have those 2 extra electrons on this side. I must have added them. So there we look at that. And then if we look at this, we can say, right, we're adding electrons. Because we're adding electrons, it is reduced. And if it is reduced, that means it is the oxidizing agent. Okay, is the oxidizing agent. So we have got full equation, Okay, we've realised that through all the colours that we worked out over there. We knew that in organic solution our iodine was purple. We knew that in aqueous solution our bromine was orange-brown. Okay, and we figured out our full balanced equation. We then did our ionic equation. We then did our oxidizing agent and reducing agent. So there's our reducing agent because the reducing agent is oxidized, and there's our oxidizing agent because the oxidizing agent is reduced. And you can work that out from just a small bit of writing like that if you just work through it step by step. We are now going to look at a new reaction with halogens called disproportionation. Disproportionation is a reaction in which the same element is oxidized and reduced. And the example we're going to go over is chlorine in drinking water. Now this is a common exam question, especially in more AS exams, but what you have to do is 3 kind of points. And so here's our exam tip for here. First of all, describe why this reaction is disproportionation. So identify the element that is being oxidized and reduced, and state that it is being oxidized and reduced, and therefore you're explaining why it's disproportionation. Identify the oxidation numbers. Now you probably need to do that before you recognize it as disproportionation, because you have to use those to recognize which one has been oxidized and reduced. Then relate this to the movement of electrons. Okay, so relate their oxidation or reduction to the movement of electrons. Now let's do chlorine in drinking water. So chlorine in drinking water is basically Cl minus aqueous, okay, plus H2O, okay, plus H2O. And then that's going to go to HClO, which is your acid, your chloric acid, plus your hydrochloric acid. Okay, so there you have chlorine plus water goes to chloric acid plus hydrochloric acid. Now we're going to look at the chlorine because you know the chlorine is going to be doing it, but normally you'd have to go through all of the oxidation numbers just to check which element is actually doing it, but we know the chlorine is in this state. So we're going to do the oxidation numbers next. So that is 0 because it's an element, and then we go to the chlorine here. Now I'm going to put all of the fixed oxidation states in purple just so you can see them. We use a process called 1,2,3 FHOCL. 1,2,3 FHOCl. Fluorine, hydrogen, oxygen, chlorine. So if you come to the element first and you look at a compound like this or a molecule like this, and you can see the element you want to find out is coming after the other elements. For example, 1,2,3 for H, or the H comes before the Cl, so therefore it will be a fixed oxidation state. The fixed oxidation state or oxidation number that we have for this is +1. It's for H, O, so the O comes before the Cl, the Cl. Okay, so therefore that will be fixed, and its fixed one is -2. We'll then go on to do the hydrochloric acid. 1,2,3 for H, so we've got the H and the Cl is at the end, so this is the fixed oxidation number. Fixed oxidation number of H is +1. We then go and do the chlorines and do it because this whole thing is neutral. So if we've got -2 and +1, to make it neutral, we need +1. Okay, to make this neutral, we need -1. Okay, so now they're both neutral, they add up to 0, and we've got our oxidation numbers. So we know that chlorine, okay, is going to go in 2 directions. It's going to go to HClO, and it's going to go to HCl. And in the HCl, the chlorine, that's going to be a -1 oxidation number. Okay, and then in this one, the chlorine is going to be a +1 oxidation number. So I've stated my oxidation numbers. Okay, and you might have to put this in a nice sentence, say the oxidation numbers are this and this. Okay, but I've done my oxidation numbers. Now I need to relate this to my oxidation or reduction. So that means, remember, I'm going from 0 to +1. 0 to +1 means I am losing 1 electron. So that's losing E minus, so it's 1 E minus. Okay, so losing 1 E minus. And this is gaining 1 E minus. Okay, so it's gaining 1 E minus. So we're losing and we are gaining 1 E minus. Just to make it clearer, if you lose 1 E minus, okay, that means you are doing oxidation. Okay, and if you are gaining 1 E minus, that means you're doing reduction. Okay, so we have oxidation because we're losing 1 E minus, and we have reduction because we're gaining 1 E minus. Of course, I would like you to do this in the exam by putting a nice sentence. Okay, so I might put a sentence like, the chlorine has an oxidation number of 0, which is moving to being chlorine in chloric acid, of an oxidation number of +1, which means it's losing 1 electron, therefore is oxidized. The chlorine is going from 0 to -1 in the hydrochloric acid, which means it's gaining 1 electron, and therefore it is reduced. Okay, and that is how you answer a disproportionation question, usually with 3 marks. We're now going to move on to our next example of disproportionation, and this time we're going to add chlorine to sodium hydroxide. What I haven't mentioned here is the fact that you make sodium chloride and sodium chlorate. This chlorate is often used as a bleach. Okay, so you see something with chlorate in, normally used as a bleach. Now we've got water as well in the liquid state. Okay, and so if we look at this and we go along and we do our oxidation numbers again, so we're in chlorine, we've got a 0 because it's an element. Okay, then we go to the chlorine here, and we can see that this is +1, therefore this should be, okay, -1, okay. So our chlorine there is -1. And look here, we've got a +1 here and a -2 here, so we go down, and we can see that this is +1, okay. So we've got a chlorine going to a -1 and going to a +1. And again, we're doing this a bit quicker because I showed you how last time to work out all the other oxidation numbers. So we can then go into the question itself, and we can do it like we did last time. Okay, so our chlorine, which has an oxidation state of 0, oxidation number of 0, okay, which is then going to go to in our sodium chloride. So in our sodium chloride, the chlorine is -1, okay, and then we go from there to the sodium chloride. And so we've got the sodium chloride there, the chlorine within there is +1, okay. And if we look at that, that means that the sodium chloride has gained, okay, and it has gained 1 E minus, okay, 1 electron. So it's gained 1 electron, and then we go to the other one, which has lost 1 electron, okay. So we've got, again, similar to what we did last time, okay, and we can then say from that, we can say gained 1 electron, therefore is going to be reduced, okay, and then lost an electron, therefore going to be oxidized, okay. So therefore this is a disproportionation reaction because we have a chlorine which has gained 1 electron, okay, because it's gained 1 electron, it is reduced. We also have chlorine which has lost 1 electron, because it's gone to the +1 oxidation number, and therefore it is oxidized. So this is another example of disproportionation. Now just something to add on to the end of that, because sometimes there is a question in the exam that asks you what the conditions are for this reaction. So the conditions are cold and dilute sodium hydroxide. Notice we've got this "and" here because you need both. Cold and dilute. It's a silly little 1-mark question, but really important to remember cold and dilute when you do the conditions. So this is our next example of a disproportionation. The last example of disproportionation is with hot and dilute sodium hydroxide. We can see here that the chlorine's gone from 0, as it has done in the previous examples, and it's gone to -1, as it has done in the previous examples again. But this time we have sodium chlorate with 3 oxygens, and therefore we have an oxidation number of +5 instead. That's because the sodium is +1 and the oxygens that are here are -2, but there's 3 of them, so it adds up to -6. So -6 on the right, and we need to make it +6. So +6 is made by +1 plus the 5 from the chlorine. But hopefully you're okay with that from the previous examples. Now, let's have a look at what this looks like in terms of an exam answer. The exam answer is chlorine is gaining 1 electron. Again, I'm writing it out this time. Gaining 1 electron. The oxidation number is going from 0 in chlorine to -1 in sodium chloride. Because it's gaining an electron, it is reduced. Then we go, chlorine is losing 5 electrons. The oxidation number is going from 0 to +5 in sodium chloride. Okay, and so is oxidized. Now, chlorine is both oxidized and reduced, so the reaction is disproportionation. So that's a full answer, which will get all your marks in the exam. Let's talk about another practice question that can be common in an exam. And this is one to confuse you, which is why we include it in the video. So 0.072 grams of an element X is reacted with 0.01 mole. Notice we've got grams here, but moles there. And it's moles of F2 to form a chloride with the formula XF3. Now, what is element X? So I'm going to show you how you go through to this. Let's get rid of the question and just highlight the important parts. So the important parts here, we've got our mass, and we've got the element X, and we've got 0.01 of F2, and we're making XF3. So if we then put the equation up, and you see balancing 2x plus 3F2 goes to 2x3. Now the way to get this wrong is to look at it and see there's a ratio of 2 to 3 and then start playing around with that 2 to 3, because what you can do is turn 0.072 into moles for each of these elements. They're the options in the question, so gallium, boron, phosphorus and aluminium. So it can be, so you could work out the moles of each of those and say, right, okay, let's see if it's a 2 to 3 ratio, and that works. That's the wrong way to do it. And the reason it's the wrong way to do it is because here we have 3 fluorine molecules, but we actually have 6 atoms. So it's 3 fluorine molecules, but 6 atoms, okay? Now, if that is the case, you can also look at this and you say, right, okay, what is the ratio of X to F here? Well, the ratio here is 1 to 3. Okay, so we need 1 part, or 1 mole X, to 3 parts of fluorine. That's fluorine atoms, not fluorine molecules. Okay, so that 1 to 3 ratio is really important. If you think about it as well, here is 3F2, but there are actually 6 fluorine atoms. Because there are 6 fluorine atoms, the ratio is still 2, if for example, atoms of X to 6 atoms of fluorine, which is still a 1 to 3 ratio. So we need to turn the number of moles of here, which is moles of F2, into the number of moles of F, or F atoms. Okay, so that means 0.01 moles of F2 will be 0.02, so times it by 2, because there are 2 atoms of fluorine for every molecule of fluorine. So that means you will have 0.02 moles of F atoms. And we need to find out whether the ratio between X, and remember, don't be confused by this 2 and 3 here, it is 1 to 3, so 1 to 3. We need to know whether these four elements, once we work out their moles, will it be a 1 to 3 ratio? So let's stick with our atoms. So we've got 0.02 moles of F atoms, okay, and we're going to start working out our number of moles of each of these elements. And we can do that by taking the mass, which is given up here in the question, okay, and we can divide it by our atomic mass, which we get off the periodic table. So here's your example. So, but we're going to cut ahead and give you all of those answers here. So if we carry on, our moles of gallium, if we did that calculation, would be 0.0103. Remember, we have 0.02 of the fluorine. That is a ratio of 1 to 19. No, 1 to 19 is not 1 to 3, so therefore that cannot be the right answer. We then go for moles of boron. If we work out moles of boron, it's 0.00667. Okay, and again, feel free to be putting this in your calculator as I do the questions. Better that you do it and not just watch the video. If you look at that, it's a ratio of 1 to 3. We want a ratio of 1 to 3, so it's in green. This is our answer. But let's do the other two just to show that that is the right answer. So we've got a moles of phosphorus. Moles of phosphorus is 0.00232. And this time the ratio is 1 to 9. And then we go to the moles of aluminium, 0.00267. And the ratio is 1 to 8. So we've got our 1 to 3 ratio is only apparent in boron. The common mistake is to look at this, to not times 0.01 by 2 and try and get a 1 to 3 ratio. If you do that, you'll end up doing the wrong answer, which is aluminium down the bottom. So this 1 to 3 ratio is really, really important. So the answer in this case is, as said, boron. Now let's move on to the benefits and uses of chlorine, often a 1-mark question in exams. The benefits, they kill bacteria. It's the same as GCSE. So they kill bacteria in drinking water, to make water safe to drink. The risks, it's toxic in larger doses and can be an irritant in smaller doses to some people. Okay, so it's important you remember both of these. And also they can mix with organic hydrocarbons to make halogenated hydrocarbons, such for example as CH3Cl. Okay, so any one of these as the benefit and the risk will be good enough to get your mark in the exam. Now we're going to look at testing for halides. Halides are the ions, so for example looking in sodium chloride or looking in sodium bromide, sodium iodide. So you're looking for those ions in ionic compounds. Now, as GCSE, it is an aqueous silver nitrate test, and you use silver nitrate and nitric acid to determine what the halide is. Now, the halide from GCSE is chloride if you see a white precipitate during that reaction. Now, slightly different from GCSE is you will be expected to do the ionic equation. So the ionic equation is here, Ag plus aqueous plus Cl minus aqueous goes to AgCl solid. So it's a precipitation reaction, creating a precipitate and a white precipitate at that. We then go on to bromide, which is a cream precipitate. Notice slight change in colour there. And then it's Ag plus aqueous plus Br minus aqueous goes to AgBr solid. We have the same with the iodide, but this time a yellow precipitate, again with a similar ionic equation. Now it's really important that you can do all these ionic equations, and really important you remember white, cream and yellow. Now, what is really important also is that you add the nitric acid to get rid of carbonates. So if you have a carbonate in there, then the acid will react with the carbonates, because a lot of carbonates are the same colours or white as these precipitates, and therefore could make your result invalid. Okay. But the extra bit that we have in A-levels is you can't really tell the difference between cream and white. Cream and white is almost impossible to tell the difference between, and sometimes even yellow is, and we'll show you what in a video in a second. Now that's why we do the following. We add dilute ammonia, and the precipitate will disappear. So if I add dilute ammonia, you'll find that the silver chloride that is produced will disappear. Okay. If I then put that up to concentrated ammonia, so concentrated ammonia, the precipitate will disappear when it's bromide. So with bromide you need concentrated ammonia to make the precipitate disappear, and with chloride you need dilute ammonia to make the precipitate disappear. Now with iodide you add concentrated ammonia and the precipitate will remain, it won't disappear at all. That means you can tell the difference between the bromide and the iodide quite easily, and the difference between the chloride and the bromide quite easily. I'm going to show you what this looks like in a video next. So we've got our test up in the corner just to remind you, so if you're not sure. Okay, and then let's look at the video. So the video here, as you can see, what I've done is I've added into here my silver nitrate, and as I add my silver nitrate, this one is my chloride, and this has got a white precipitate. And you can see as you go across here, it looks slightly cream. Okay, and you see across here, can you see the colour looks really similar? This is why we have to use ammonia, because this is meant to be yellow. This is iodide, it's meant to be yellow. Okay, this is bromide, it's meant to be cream. Now, Here I've added the dilute ammonia, and you can see that instantly that precipitate has gone predominantly. There's a few tiny bits, but it's gone, okay? We then add concentrated ammonia, and you can see again, its majority of it has gone. There's a tiny bit remaining, but it's disappeared, it's dissolved, okay? And then we have a look at here, and we've added concentrated ammonia again, but there's no change. You can see there is no change whatsoever. What I'm going to do is then come in with a stirrer here and just mix these all up to try and show you definitely that everything is gone. You can see there's a tiny bit there, but it's all gone, okay? And you can see there's such a major difference between the dilute ammonia that's been put in here, the concentrated here, and the concentrated here. And we can see it doesn't disappear for iodide, disappears for bromide, and disappears for chloride. So I realise that going through a video, it's very, very quick. So I'm just going to show you those pictures again, okay? So those pictures look like this. So we've got our initial solutions, and we've got our chloride, bromide, iodide, just in order, in the same order as we've got over the other side of the page. We then add our silver nitrate, and we should have our white precipitate, our cream precipitate, and our yellow. Now, the yellow and the cream are almost impossible to tell the difference between. So what we then do is add our dilute ammonia, and therefore the precipitate disappears for chloride. We add our concentrated ammonia, and the precipitate disappears for bromide. And then we add our concentrated ammonia, and the precipitate remains, does not disappear, for our iodide. And that is the reactions you can use to tell the difference between chloride, bromide, and iodide. And this is how it actually looks when you do it in your laboratory at school. Okay, and this is why you have to use ammonia, because a lot of these colours look very, very, very similar.